welcome to the fourth session on support vector machines. In our previous session, we talked about various objective functions under optimal margin classifier, and we made use of Lagrangian for dual formulation to come up with an efficient solution. Further, so far in our discussion, we focused upon linearly separable data sets. In our first class of SVM, if you remember, we introduced the concept of outliers. We stated that maximum margin classifiers are sensitive to the outliers, meaning they will not perform well in these situations. Here, these outliers are actually the noisy samples in the data set. In fact, in many real-world problems, we may come across the data which is noisy. So, we may not have a linear decision boundary that can separate out the positive and negative observations. So, in this session, we are going to discuss how SVM deals with noise. Now, let us see how we formulated our linear SVM earlier. In simple words, we wanted to find W and B. Those are the parameters for the hyperplane. W is a vector known as weight vector. So, we want to find W and B such that the margin 2 divided by norm of W is maximized. For each of n training examples such as xi, yi, subject to yi into W transpose xi plus b is greater than or equal to 1. You might have a question how we computed this margin as 2 divided by norm of W. So, let us have a discussion. So, once again, let us consider our example wherein we are having positive samples and negative samples. Those are described with two features x1 and x2. The positive samples are denoted as class y equal to 1, whereas the negative samples are denoted as class y equal to minus 1. We have a separating hyperplane as shown and denoted as W transpose x plus b equal to 0. Please note, W is a vector that is orthogonal or at 90 degrees to the separating hyperplane. Now look at these positive and negative samples. These are actually the support vectors. And as we know, there are two parallel lines. Those actually pass through the support vectors of opposite classes. So, the line that passes through the positive support vectors is denoted as W transpose x plus b equal to 1, whereas this dashed line that passes through the negative support vectors is denoted as W transpose x plus b equal to minus 1. And the distance between those dashed parallel lines, those are actually passing through the support vectors of opposite classes, is the margin, and this margin is 2 divided by norm of W. So, you might be interested in how we computed this distance as 2 divided by norm of W. So, let us obtain this distance mathematically. We know the geometric margin. So geometric margin gamma I is given as yi into W transpose divided by norm of W into xi plus B divided by norm of W. This geometric margin gives us the distance of an arbitrary sample xi from the hyperplane. Now let us assume that this positive support vector is denoted as S1, and if we try to compute the geometric margin from S1 to the hyperplane, it is denoted here as gamma 1. So if we drop the perpendicular from S1 to the hyperplane, it will provide us the geometric margin gamma 1. Similarly, let us assume that this negative support vector is S2, and if we drop a perpendicular from this S2 to the hyperplane, it denotes the geometrical margin denoted here as gamma 2. Thus gamma 1 is distance of positive support vector from hyperplane, and gamma 2 is the distance of negative support vector from the hyperplane. And we are interested in computing the margin gamma, which is equal to gamma 1 plus gamma 2. In this expression of geometric margin, this yi is nothing but a class. In our case, it is either plus 1 or minus 1. So now we can write the expression for gamma 1 is equal to 1 into W transpose divided by norm of W into S1 plus B divided by norm of W. So this is the distance from point S1. Similarly, we can compute the distance from point S2 as gamma 2 equal to minus 1. Now minus 1 is the label for S2, that is the negative sample, into W transpose divided by norm of W into S2 plus B divided by norm of W. And as I mentioned, we are interested in computing gamma 1 plus gamma 2. Now by adding these two terms, gamma 1 plus gamma 2, we get W transpose divided by norm of W into S1 plus B divided by norm of W minus W transpose divided by norm of W into S2 minus B divided by norm of W. Here these two terms, B divided by norm of W minus B divided by norm of W, will get cancelled, and what remains is gamma 1 plus gamma 2 equal to W transpose divided by norm of W into S1 minus S2. Now as we know, this S1 lies on this plane W transpose X plus B equal to 1, hence S1 satisfies the equation W transpose S1 plus B equal to 1. Similarly, S2 lies on the other line, that is W transpose X plus B equal to minus 1, and hence S2 satisfies W transpose S2 plus B equal to minus 1. Now let us give number 1 and number 2 to these two equations. And now if we subtract equation 2 from equation 1, what we get is W transpose into S1 minus S2 plus B minus B is equal to 1 minus minus 1. So it comes out to be W transpose S1 minus S2 equal to 2. Now by substituting this in our earlier expression of gamma 1 plus gamma 2, what we get is gamma 1 plus gamma 2 equal to 2 divided by norm of W. And this is the distance between these two lines, those pass through positive and negative support vectors. And we would like to maximize this margin 2 divided by norm of W. Now you must have understood how we got this margin as 2 divided by norm of W. And while formulating linear SVM now, we said that we would like to find W and B such that 2 divided by norm of W is maximized for each of n training examples of the form xi yi subject to yi into W transpose xi plus b greater than or equal to 1. Or the another way to formulate the problem is find W and b such that norm of W square, that is equal to the dot product of W and W, or it can also be written as W transpose W, is minimized for each of n training examples of the form xi yi subject to yi into W transpose xi plus b greater than or equal to 1. This formulation enables us to deal with only those training instances which are linearly separable. But sometimes it may happen that we are having the data that is not linearly separable. The present formulation of linear SVM is sometimes known as hard margin SVM. In hard margin SVM, we assume that all positive points lie above the plane denoted by W transpose x plus b equal to 1, and all negative points lie below the plane W transpose x plus b equal to minus 1. And this can be written as the constraint yi into W transpose xi plus b greater than or equal to 1. So even though the previous formulation will help us to efficiently classify the linearly separable data, there is some limitation of this formulation. So what is the limitation of this formulation? So the question is, what if the data is not linearly separable? That means no linear function or hyperplane is available to separate out the data. Or what if the data is noisy? So please look at this figure. So what we have here is the data points from two classes are being mixed up together, or as we can see here, few positive samples are mixed up with the negative samples, and few of the negative samples are very close to the positive samples, and the data cannot be separated using a linear hyperplane. One of the reasons why we are having such kind of a data is the data has noise, or few of the data samples are outliers. So if we would like to deal with such kind of a noisy data, what to do? We need to extend the definition of maximum margin to allow these exceptions. So we will extend the definition so that we can allow these non-separable points. So we have to redefine our objective function now. Earlier, our objective function was trying to maximize the margin or minimize the dot product W dot W. But now this will not be sufficient. So we have to be able to have a decision boundary or a decision surface that makes some errors. So if we have such noisy points, we need to find the decision boundary which does not clearly separate out the positive and negative points. So there would be some error in classification, and we need to allow such misclassification. But now if we are allowing such misclassification or error, then we cannot satisfy the constraints those we defined in the earlier formulation of SVM, and hence we have to make some modifications in our earlier formulation to accommodate such noisy samples. So while making modifications, we need to consider modifying the objective function. So one way of looking at this problem is we would like to define a decision boundary that maximizes the margin and also reduces the error or reduces the number of misclassifications. That is, we would like to minimize the training error. So now while dealing with noise in the data, we need to modify our objective function something like this: W transpose W plus the training error. Also, we may think of using a parameter C to control the contribution of this error. So while looking at the alternative solution, let us try to understand what actually we are going to do. So once again, look at this figure, and we have few positive samples and few negative samples. But as we have seen earlier, we are having the noisy points in the data, and as in case of linear SVM, we are having the hyperplane denoted as W transpose X plus B equal to 0. Also, we are having two parallel lines, one towards positive samples and one towards negative samples. Those are denoted as W transpose X plus B equal to 1 towards positive samples and W transpose X plus B equal to minus 1 towards negative samples. And as we have seen earlier, the margin between these two lines is denoted as 2 divided by norm of W, or it is equal to 2 divided by square root of dot product of W and W. Now as we can see here, for few of the points we have an error. For example, these two negative points ideally should be on the other side of the margin. So this negative point and this negative point are contributing into the error. Similarly, we are having two positive points. Those also are contributing into the error, because these points ideally should be on the opposite side of the margin. So corresponding to each of these points which are not correctly classified or which are misclassified, assuming a particular decision boundary and the corresponding margin, for each such point we can introduce some penalty, and the penalty can be like it is proportional to the distance, meaning how far it is from its correct position. For example, if we consider this negative data point which is misclassified, I'll look at how far it is from the actual margin, meaning for this point to be classified correctly, I need to shift this point by this minimum distance so that it can be correctly classified. So if I drop a perpendicular from this point to the appropriate margin for the negative class, then I get some value for the distance. Similarly, for all the points those are misclassified, I can obtain the minimum distance that the point need to be moved so that the point can be classified correctly. So this quantity that we have computed as a distance can be treated as an error or penalty, and we associate a variable known as slack variable to this distance. So let us once again look at the figure. If this negative point is say 0.1, then associated with this 0.1 which is misclassified, we are having a slack variable zeta 1. Similarly, corresponding to this point, say 0.2, we are having associated this slack variable zeta 2. Similarly, with these two positive samples, we are having the slack variables associated as zeta 3 and zeta 4. So, these are the penalties that we have associated with the points. Those are at wrong positions or those which are misclassified. Obviously, the zeta values associated with the points those are classified correctly will be equal to 0. So now simply we are writing our objective function to be minimized as the dot product w.w plus c multiplied with distance of erroneous points to their correct zone. And to rearrange this in a systematic way, we are making use of the slack variables zeta i's to denote the distance. These zeta i's allow misclassification of difficult or noisy examples. So, we will rewrite our objective function to be minimized as half into w.w plus c into summation over k equal to 1 to n zeta k, where n is number of training examples that we have. As we are having n training examples, we are having n constraints. So, the constraints are like y transpose xk plus b greater than or equal to 1 minus zeta k if yk equal to 1, that means a positive sample. And for the negative sample, w transpose xk plus b less than or equal to minus 1 plus zeta k. So, instead of having two separate constraints for positive and negative samples, we may put it together. And now we can write the constraint as yk into w transpose xk plus b greater than or equal to 1 minus zeta k for k equal to 1 to n, and zeta k values should be greater than or equal to 0 for k varying from 1 to n. This means zeta k value would be greater than 0 if the sample gets misclassified, or it is equal to 0 if the sample is classified correctly. So, this is the formulation of the maximum margin classifier. Whenever we are having the noise and we are supposed to minimize half w.w plus c into summation over k equal to 1 to n zeta k with the provided constraints. Here, C controls the relative importance of maximizing the margin and fitting the training data. After formulating this objective function, what's next? We need to solve this equation, and how we are going to solve this? We can make use of Lagrangian to solve this equation. Now, let us see the Lagrangian of our objective function. So, the Lagrangian of our objective function is written as Lagrangian with the parameters w, b, zeta alpha beta is equal to half w dot w plus c into summation over I equal to 1 to n zeta I plus summation over I equal to 1 to n alpha I yi into w transpose xi plus b minus 1 plus zeta I minus summation over I equal to 1 to n beta I zeta I. As we have seen, we are having two kinds of constraints here. So, n number of constraints of one kind and n number of constraints of another kind. So, total 2n constraints we are having here, and alpha i's and beta i's are the Lagrangian multipliers. Those are greater than or equal to 0. Now, once we obtained the Lagrangian of our objective function, let us see now how to find out the dual formulation corresponding to the Lagrangian. Similar to that of the dual formulation for linear SVM, we are having similar kind of dual formulation. So, we are finding out alpha 1, alpha 2 up to alpha n such that to maximize j of alpha, that is equal to summation over I equal to 1 to n alpha I minus half summation over ij equal to 1 to n yi yj alpha I alpha j xi transpose xj. So, this expression for dual formulation is same as that we have seen earlier for linear SVM. Only difference is in the constraints. So, for linear SVM, we had the constraints alpha I greater than or equal to 0, I varies from 1 to n, and summation over I equal to 1 to n alpha I yi equal to 0. So, these were the constraints in linear SVM. Now, as far as SVM with noise is considered, we are having the first constraint which is changed. So, the first constraint is alpha I lies between 0 and c for varying for all the samples n. The second constraint remains the same. So, you must have observed now the dual formulation for normal linear SVM and the dual formulation for SVM with noise. We are having the same formulation except one constraint. In regular linear SVM, the constraint was alpha I greater than or equal to 0, and here in SVM with noise, we are having modified constraint as alpha I lies between 0 and c. This kind of formulation is also called as soft SVM because we do not have a hard classifier or a hard decision boundary that clearly separates the positive and negative points, but in this formulation we are allowing the error and we are allowing few noisy points. And now let us try to find out the solution for this dual formulation of soft SVM. So, we are having now the soft margin classifier. Please note that the samples such as Xi's which are having non-zero alpha i's are the support vectors, and the solution to this problem is given as W is equal to summation over I equal to 1 to n alpha I yi xi. Once again, this is similar to that of our normal linear SVM. And B is given as B equal to yk into 1 minus zeta k minus summation over I equal to 1 to n alpha I yi xi transpose xk for any k, subject to this alpha k is greater than 0. As I mentioned, alpha I is non-zero only for those points which are support vectors, and once we find the values of alpha I, we can find the value of B. So after finding out the solution, it is used for classification. So we are using here the similar formula g of x equal to summation over I equal to 1 to n alpha I yi xi transpose x plus b. Here this x is the test sample, and we need to compute the dot product of the test sample with our support vectors. Once again, note that there is no need to compute w explicitly. We can observe that this formulation is really very simple and straightforward and easy to apply. If this g of x is evaluated as positive, it is a positive sample, otherwise it is a negative sample. So this is how we can deal with soft classification or soft SVM. Please note, in this soft SVM, the decision boundary or the decision surface is still linear. Using this formulation, it is not possible for us to handle the cases where the decision surface actually need to be non-linear. How to handle such cases we are going to discuss in our next session. So let us stop today. Thank you.